Hello everybody. This is the second lecture of the ship theory series. We are looking at the general theories on the ship theories. Today we are going to talk about I'm going to talk about the Bernoulli theory and the eductor system. So in the previous lecture we talked about the pressure. We saw that there are two types of pressures. One is hydrostatic pressure and the other one is hydrodynamic pressure. Please go through my first lecture regarding this hydrostatic and hydrodynamic pressure, then you get an idea what these two are. Now this is a basic eductor system. In order to explain the Bernoulli theory, it would be much more easy to use the ship equipment itself. We have onboard eductor systems. Later on I will basically tell you where are these eductor systems are used on board. So this is basically a pipeline. Here you can see the thickness of the pipeline, or the diameter of the pipeline is larger compared to this side, and there is a reducer, and it reduces the pipe into a smaller diameter. So, and let's say a pump is there. This is a pump, and from this pump, from the sea, water will be taken in from the sea, and water will be sent into this pipeline, and again it will go back to the sea. So sea to sea, the water will be transferred. So here you can see that this water, when it goes through this bigger pipe, it has a certain velocity, and it will be squeezed here because there is a reducer. It will be squeezed here, and now it will go in another different velocity. So there was a person called Bernoulli. He said that at any given place, if we take the cross section of this pipe, we take cross section, at any given place, here or here or here, doesn't matter, at any given place, Bernoulli said, if we add the hydrostatic, I will write it in this way, the hydrostatic pressure and the hydrodynamic pressure equals to a hydrostatic pressure, hydrodynamic pressure equals to a constant. Let's put 1 and 1. So again, if we apply the same theory here, again at this point, hydrostatic pressure and hydrodynamic pressure adds to a constant. But as for the Bernoulli's theory, since there are no any, assume that there are no any energy reduction. Let's assume that there is no any friction in this pipe, and if the friction is there, energy will be reduced. So assume that there is no any energy reduction and there are no any energy decay. The energy does not decay in this pipeline. Then, as per the Bernoulli's theory, this point and this point, the addition of hydrostatic pressure and hydrodynamic pressure equals to the constant. Here also hydrostatic pressure and hydrodynamic pressure equals to the constant. These two constants will be same. They are same. But that does not mean that hydrostatic pressure here and the hydrostatic pressure here should be same. It doesn't need to be. Let's assume that the hydrostatic pressure here is, assume let's say this is 70, for example, this is 70 and this is 30, whatever the unit is, doesn't matter. Let's assume that this is 70 and this is 30 and it will be equals to 100. But that does not mean that here it should be same 70. It can take a different value. For example, it will take, let's say, 60 or 50, and 50 equals to 100. As long as this 100 and this 100 is same, but as per the Bernoulli theory, this 100 and this 100 should be same. So this k and this k will be same. So now if we look at the velocities here, now we have to focus here at the hydrodynamic pressure, not the hydrostatic pressure, but first we will focus on the hydrodynamic pressure. Right. So hydrodynamic pressure can be given as just 1 plus hydrodynamic pressure can be given as, let's assume that this, at this point, the velocity of the water is v1. At this point, the velocity of the water is v2. These two are not going to be same, because here when you squeezed in, because of this push, this velocity is going to definitely increase. v1 is less than v2. When this is getting squeezed in, when this water column is getting squeezed in and get pushed, the velocity should increase. So that means v2 is more than v1. v2 is more than v1. Right. So now if we put this one into the hydrodynamic pressure, you know that from the previous lecture, hydrodynamic pressure can be given as half rho v1 squared. Here in this case, hydrodynamic pressure can be given as half rho v2 squared. But it should be equals to the same constant. Constant cannot be changed. But you can see from here that v1 is less than v2. v1 is less than v2. Here v2 is more than v1. So the whole hydrodynamic pressure increases. It increases compared to HD1 or hydrodynamic pressure 1. So here the dynamic pressure increases compared to here. But as per the Bernoulli's theory, K needs to be maintained, or this constant needs to be maintained. So in order to maintain this constant, what should happen to HS2 compared to HS1? Assume that this is going up, this one is increasing, but this one needs to be maintained. So when this is going up, this one should come down. When the dynamic pressure increases, hydrostatic pressure should decrease. It should come down. So at this point, if you look at this point, the hydrodynamic pressure is increasing. You can see that because V2 is higher than V1. When V2 is higher and it is going up by squared value, it goes up very high. So HS2 should reduce, or the static pressure here should reduce compared to here. So when the static pressure reduces here, let's say this is the pressure here P, I would let's say this is the pressure here, P. This is the static pressure, okay? So this static pressure, this is static pressure, P, right? This is the pressure P, and this P will go down, or the static pressure here it goes down as the velocity increases. If we increase the velocity furthermore, this goes down furthermore. Now this is a pipe eductor system and this is a ballast tank, right? Now you can see the pipe is, this pipe is not touching the water itself. This pipe, this is the ballast tank, this pipe is going to the ballast tank, this is a suction pipe of the ballast tank. This pipe is not touching the water itself, you can see it from here, and this is the air vent, right? This is the air vent. Now what should happen to this water? Will it go up, and can there be a suction created here, or just remain there, nothing will happen, right? What should happen here? Let's see what will happen. Now the pressure here is the static pressure, it is getting reduced, but you can see because of the air vent, the atmospheric pressure, remember pressure is a force, always remember pressure is a force. Now force is getting reduced, is here force, atmospheric pressure is not getting changed now. So atmospheric pressure is now acting on top of this liquid or inside this tank. Atmospheric pressure is there inside this tank. What if now here this is atmospheric pressure, right? This is static pressure of this liquid and this is atmospheric pressure now acting, right? So can it be a suction here created now? Will there be a suction created here? No, actually there is no any suction in anywhere. Even though we are using the word suction for our easy reference, there is no any suction, it's actually always a push. You can see this P, if this P is less than atmospheric pressure, what will happen? Atmospheric pressure push everything to up, atmospheric pressure. If this P is less than atmospheric pressure, if this P is less than atmospheric pressure only, atmospheric pressure will push everything up, then only. So there is no any suction created here, instead always a push. So in this case, when the air is getting pushed up, even these water molecules will go up. So you don't have to prime this eductor system like in a centrifugal pump where you have to prime the system, you have to fill the water and prime the system. Here you don't have to prime anything, because as long as your vent is good, air vent is working good, and the atmospheric pressure is coming inside, and the velocity should be such that this pressure should reduce less than the atmospheric pressure. This pressure should reduce less than the atmospheric pressure. That's why near the eductor there is always a pressure gauge. Somewhere here there is a pressure gauge where it should go less than the pressure gauge should go less than the atmospheric pressure. And there are two types of pressure gauges, absolute pressure gauges and relative pressure gauges, where absolute one will show 1 and 0. In between 1 and 0 will be the less than vacuum, less than atmospheric pressure pressures will be shown. This is 1 is atmospheric pressure, this is absolute one. In relative one, pressure gauge will show 0 and minus. So it doesn't matter what type of pressure gauges you are using. In any case, this pressure should go less than atmospheric pressure. Otherwise, if in any case, if it is equals to each other, nothing will happen. If it equals to each other, nothing will happen. This water will go and nothing will happen to this water. If in any case P is more than atmospheric pressure, you will be filling the ballast tank. So make sure that when you are operating the eductor system, the most important factor here is that your air vent should be in very good condition, and if it is in older ships, it needs to be opened up manually. This should be in very good condition. The air vent of the tank should be in very good condition, so that atmospheric pressure can come in and give the required push to send this water up. And the next requirement is that this velocity of the water should be such that this pressure should go less than the atmospheric pressure. Then only the eductor system will work in a good manner. Right. Now, examples. Where can we find this eductor system in a ship? Of course, you can find the eductor system in bulk carriers. For example, when you are stripping the tanks, eductor system is used because you don't have to prime the system. The priming is not required, right? In bulk carriers, you can find the eductor system. Plus, in the fire line, for example, let's say you have the bosun store forward. In the bosun store, you have bilges in the bosun store. These are the bilges in bosun store. Forward bosun store or forecastle store or whatever it is. These bilges, sometimes you have this fire line coming out on the deck, and it goes through the hose pipe, and the water goes out from the hose pipe. But at the same point, you have another branch coming into the bilges, where there is a eductor system here. In order to pump out these bilges, you have to send water through your fire line. This is fire line. You have to send water through this fire line, and it will be going out from the bilges, and this water will be pushed up, right? This water will be pushed up by this eductor system. And remember that before opening this valve, the static pressure here should drop more than the atmospheric pressure. If it is not less than in the sense the static pressure should drop less than the atmospheric pressure, then only this water will pushed up. Otherwise, you will be filling the bilges system. If your static pressure is more than, or the pressure here is more than the atmospheric pressure, you will be filling up the bilges system. And you can see in ships there is another firefighting equipment called foam monitor system, where you have a nozzle like this, and this is getting connected into the fire line, and a branch is taken out and will be put into a FFF foam can. So this is also eductor system where this water through the fire line is getting pushed out, and there are holes here, right? So if this eductor system, in this eductor system, again pressure drop occurs here, and this AFFF will be pushed up and get mixed up with the air, and foam will be created. So this is also eductor system that you can find on board, that the foam monitor system is also eductor system, right? So, and you can see on board ships, when some people are operating this one, they straight away connect this one, connect the fire hose into this nozzle, and straight away they put this branch into the AFFF, and then they open the valve. And what will happen? This water, since there is this pressure has not gone down the atmospheric pressure, what will happen? The seawater will come through this into the AFFF can and filling up the AFFF can, right? So it should not be done. What should be done is that you should not put this branch immediately. First you send some water at a certain velocity, it should go out, you open up the valve, increase the velocity of this water, then when after this pressure drops less than atmospheric pressure, only you put this branch inside. Otherwise, if you have an unwritten valve here, then it's okay, then nothing will come in, instead it will go up only. So this is the again a eductor system that you can find on board. So if we go back to the eductor system again, so we can come into two conclusions here from the Bernoulli's theory. Number one conclusion is that if velocity increases, pressure drops. So if velocity increases, pressure drops. This is the most important conclusion that we have to come through this Bernoulli's theory. If velocity increases here, the pressure is getting dropped, and this is the most important conclusion, because you will see in the later lectures that the pressure system around the ship is totally based on this theory or this phenomena. Our ship motion, in shallow water, for example, shallow water, deep water, in ship handling, this is the most important phenomena, that if the velocity increases, pressure drops. The vice versa is velocity drop, pressure increases relatively. And the second conclusion is that you can see this is V2 squared. So if you change the velocity by a small amount, pressure is, this hydrodynamic pressure is getting, because squared, so you change the velocity by a small amount, since this is squared, it goes up and down by a big amount. It goes up and down by a large amount because it is squared, and that means the pressure drops or pressure increases, the static pressure drops or pressure increases by a large amount. So you change the velocity by a small amount, but the pressure will go up and down by a large amount. This is the other conclusion. So number one conclusion, velocity increases, pressure drops. Number two is velocity change by a small amount, pressure goes up and down by a large amount. That is why if the ship, for example, interaction, when the two ships are in an interaction motion, passing each other in interaction motion, if you change the velocity by a small amount, the whole pressure system change by a very big amount. You change the velocity by a small amount, you change the pressure system by a big amount. So that is the second most important conclusion. Okay, thank you. We'll look into in the next lecture we will look into the other details, the pressure system around the ship. Thank you very much.